In the previous lecture, we went through the relationships between different parts of a drivetrain for the series hybrid vehicles, from the engine through a gearbox to the generator to the battery to the electrical motor, then from electrical motor through another gearbox to the wheels, and then from wheel to the vehicle speed. So there's a lot of calculations, a lot of formulas between different conversion factors of the forces and the torque and the velocity and also the power. But bear in mind, there's really two key elements there. One is the conversion between two sides of a gear set. The conversion of where the torque is increased or the velocity is reduced. And also the conversions between the input and output of a system in relation to the efficiency factors. Okay, just these two really just the key factors that you need to consider, and you won't get too much problem with your calculations. And bear in mind always the input power is always higher than the output. But whatever you can actually, depends on what you know. You can actually work out either input or the output power, depending on what you know, and then use the efficiency factor to work out the other power as well. So really fairly straightforward process, although the number of equations may look quite complex. Okay, but the relationships, they are really just two simple relationships. Relationship between the gear sets and relationship between input and output power of a subsystem or of a component. To help you tie up these relationships, I'm going to use this example to demonstrate how the calculations can be made. So in this example, these are the known parameters. Okay, a series hybrid vehicle is traveling at a speed of 72 kilometers per hour. That's a vehicle speed. Okay, that's forward speed. The engine is running at a speed of 300 RPM. RPM stands for revolution per minute. That means how many turns it goes through. It goes through every single minute. The output torque of the engine is 100 Newton meter. So that's the car, that's the engine. The gear ratio between the engine and the generator is 0.5. That means actually it's speeding down. Okay, but that's because the particular generator we have. The electrical motor, the output torque is 20 Newton meter. That's used to drive the wheels. The gear ratio between the motor and the wheels is 6, and the radius of the wheel is 0.4. Assuming that we know the efficiency factors as well, for the motor and the generator both have 0.95 efficiency factor, or 95%. The engine is much lower. Okay, the efficiency factor for the engine is quite low, which is 20%, 0.2, which is probably on the lower end of a typical engine. Okay, engine is probably efficiency is around 20 to 30. It's burning fuel and it doesn't produce much energy, unfortunately. So my question here is, I'm not really setting up 1, 2, 3, 4 questions. I'm just saying, what kind of parameters can we work out from all this data above? Okay. And the answer is, again, a lot. But before we do that, I want to convert all the values, because all the parameters are given here. are not necessarily all in the standard SI unit. So I'm going to convert everything into standard SI unit before I do my calculations. So vehicle speed is 72 km per hour, but our standard SI unit is meter per second. So the conversion is quite simple. Just in case you got a bit rusty with unit conversions, kilometer to meter, that's in the numerator. So 1 kilometer equals to 1,000 meters. So I put a 1,000 in the numerator terms. Hour to second. 1 hour is 60 minutes. 1 minute is 60 seconds. So 1 hour equals to 3,600 seconds. And because it's per hour, that's in the denominator. So I'm putting 3,600 in the denominator. So should end up with a unit of meter per second. So 72 times 1,000 divided by 3,600, that'll give me 20 meter per second. So the vehicle speed of 72 km per hour is the same as 20 meter per second. But that's in standard SI unit that I can use. The radius of the wheel or the tire is 0.4, which is in meters, so I don't need to convert that. The speed of the engine, or the rotational speed of the engine, is defined as 3,000 RPM. That's revolution per minute. Again, we need to convert that into a standard SI unit. For the angular velocity, the standard SI unit is radians per second. Now, revolution per second, that's revolution divided by, revolution per minute, that's revolution divided by minutes. Okay, so on the top is revolution. One revolution is one cycle. One cycle, that's 360 degrees. 360 degrees in radians, that's 2 pi. So I'm going to put the 2 pi on the top. Per minute, 1 minute is 60 seconds. That's in the denominator, so I'll put the denominator there. So 3,000 times 2 pi over 60, that'll give me approximately 314 radians per second. So again, I've got that into standard SI unit. So these are the two basically you need to convert. The torque from the motor is 20 Newton meter, that's standard SI unit. The torque generated from the engine is 100 Newton meter, again that's in standard SI unit. Gear ratio between the between the motor and the wheels is 6, that's K naught equals to 6. Kg is the gear ratio between the engine and the generator, that's 0.5. The efficiencies are defined as eta G, that's the efficiency of generator, is 0.95. Eta M, that's efficiency of the motor, is 0.95. And eta E, that's efficiency of the engine, that's 0.2. These are the parameters, everything we know now. So we got everything. Now we can actually do some calculations. So think about the engine. We know the torque, which is 100. We know the velocity, angular velocity, which we converted into sorry, I skipped that one slide. I don't know why, but anyway, I just copied all the parameters down here. Okay, and now start to do my calculations. And I started with the speed and torque calculations. So we know the forward velocity or forward speed of the car, which is 20 meters per second. Therefore, the rotational or angular velocity of the wheels will be V over R. R is a radians. So 20 divided by 0.4, that'll give me 50 radians per second. Because we know this, we know the velocity, angular or rotational velocity of the wheels, and then we know the gear ratio as well. Therefore, the motor will have an angular velocity of k0 times omega w. K0 is 6, so 50 times 6, that's 300 radians per second. So that's speed. The torque of the wheel can be calculated from the torque of the motor, because we know the output torque of the motor is 20 Newton meters. So the output torque, or the torque at the wheel, equal to the gear ratio times the output torque of the motor. Gear ratio is 6, Tm equals 20, that's 120. Now, because if we know Tw, that's the torque of the wheels, then we can actually work out the traction force to drive the vehicle, okay, which is torque of the wheels divided by the radians. Okay, so it's 120 divided by 0.4, that gives me 300 Newton. It's not a lot, but that's probably for a small car. Okay. The torque of the generator, that's the input torque of the generator, can be calculated from the output torque of the engine and the gear ratio, kg. So kg 0.5 times Te, that equals to 100 times 0.5, that gives me 50 Newton meters. The rotational velocity or angular velocity of the generator can be worked out from the velocity of the engine divided by the gear ratio. So that's omega E divided by 0.5, that will give me 626 radians per second. So you see, given all these parameters, I can work out a lot of other parameters as well. All I've done here is basically use gear ratio relationships and also the conversion between the rotational velocity to the forward velocity or other and the force and the torque relationship of the wheel. Okay, that's all I've used. I can also do another calculation for the power. I know the output torque of the engine. I know output velocity of the engine. So torque times angular velocity equals to the output power of the engine. Okay, so torque is 100, angular velocity is 314. Therefore, that will give me 31,400 watts. That's the output power of the engine, which is mechanical. Now I can put that into kilowatt as well, which will be fine as long as I keep every other power to the kilowatt for my calculations. Then it should be okay. Now the output power of the engine is 31.5 kilowatts. Efficiency of the engine is 0.2. Then of course the input has to be a lot higher to get 31.5. Therefore, the input power to the engine needs to be the output divided by the coefficient in order to get the higher number. Okay, so that's the way to remember it, whether it's divide or multiply. Okay, so input equals to the output divided by the efficiency factor, or output power equals to input power times efficiency factor. So now we know the input and output power of the engine. And for the generator, we can actually work from our way through the system. We know the engine now, so for the power of the generator, the input is coming from the engine through the gearbox. But we said previously we can neglect the power loss in the gear sets. Therefore, the output power of the engine equals to input power of the generator, which is mechanical. So PG, mechanical equals to Tg times omega g, or the mechanical power of the engine. That's same as the mechanical power of the engine. That's output from the engine. This is input to the generator. They are the same, 31.5 kilowatts. The output power of the generator would be electrical. It produces voltage and currents. But that's all we need to do. We don't really need to know the speed, rotator speed, or omega g, because we know the input power. So we just use input power times the efficiency factor. So 31.5 times 0.95, that equals to 29.9. The motor, however, now don't jump from the generator to the motor straight away, because there's a battery in between. We don't know how much it is used to charge. But go from the other way around, because we know the torque of the motor, which is 20. We know the angular velocity of the wheel of the motor as well, which we worked out previously. If I just go back there, omega m, that's 300. So it's 20 times 300. That gives me 6,000 watts, or 6 kilowatt. So in this case, mechanical power of the motor, because the motor is used to drive the wheel, so it is output. Input will be electric. Electric will be higher than the mechanical. And the input power equals to output divided by the efficiency factor. So 6 kilowatt divided by 0.95, that gives me 6.3 kilowatts. That's the input power of the electrical motor. The difference between the output power of the generator and the input power of the motor will be the power going into the battery. If it's positive, if it's negative, then it's coming out to the battery. So it's power of a generator, electrical power of the generator, which is 29.9, minus electrical power of the motor, which is 6.3. So that will end up with 23.6 kilowatts. Now, the other thing to help you to remember is that because battery power is electric, it doesn't take mechanical power. It's not a motion. Therefore, it's a subtraction between two electrical powers. It's the electrical power of the generator minus electrical power of the motor. So that will end up with 23.6 kilowatts. So we can actually work out the power of every single component. From there, we can also work out the overall efficiency of the system. The input power, the total input, is the input power of the engine. The output power, the final output power, will be power at the wheel or the mechanical power of the motor. So P naught in this equation, in this green box, P naught is the mechanical power of an electrical motor. PB is the battery power, and all others will be the efficiency factors of different components. Okay, so we have eta G, eta E, eta M. We all know these values: 0.5 for eta G, 0.5 for eta M, 0.2 for the eta E. And in the bracket, that's 1. That's eta M, which is 0.95. PB is the power of a battery, which is 23.6. At the bottom, in the denominator, P naught. P naught is the output power of the motor, or the power of the wheels, which is 6 kilowatts. So it's a 6 there, plus efficiency factor of the motor, that's 0.95, times PB, again, battery power, that's 23.6. Put everything together, we end up with an overall efficiency of 0.038. Now, you might wonder, what is so good about this car or this vehicle if the efficiency is so low? Well, efficiency is so low, it is because two factors. One, the efficiency factor of the engine, which is 0.2. So the overall efficiency can't be more than efficiency of individual components, because we have other losses to consider. So that's 0.2. So the best you could, if everything else works perfectly, the best efficiency you could get is 0.2. That's partly why the traditional or the conventional series hybrid vehicles have their own limits, because the efficiency of the engine can never be any good. The other factor why this efficiency is so low is because a lot of energy is used to charge the battery. So the energy is actually stored, it's not lost. It just because power is instantaneous. So at this particular time, under this particular condition, the generator produces power, electrical power 29.9, but motor is only use 6.3. So you would be charging the battery. The rest of it is used to charge the battery. So energy gets stored. Okay, it's not wasted. Just at that time, the efficiency appears to be quite low. But at other times, once the battery is charged up, the control system might decide to switch the engine off. Say, actually, we don't need the engine. We can use the battery alone. Then the efficiency will go up. Okay, but efficiency, the calculated efficiency at the moment is basically instantaneous. It changes over time. Okay, so that's another reason why the overall efficiency appears to be low. Okay, just the conditions the vehicle is working under. So that's my example, and I think I set two examples. That's still part of the practical questions. That's P2A, but the previous one I gave you was question 1, and over here we have question 2 and question 3. Now question 3 is very similar to my example, just work out the conversions and work out different values. Question 2 is actually you need some knowledge from the previous one on the general motion of equation of motion, the Newton's law, but you need to convert the motor output torque into the traction force, F. Okay, I'll also give you some parameters about air drag as well. So you can actually use this to work out the cruising speed and rolling resistance, that kind of stuff. Okay, and that's so to answer question 2, you need the previous general mathematical model or the general case for vehicles, the dynamic motions, and also these specific equations we use for hybrid electrical vehicles. Okay, second part should be fairly straightforward. Question 3 should be fairly straightforward. Okay, so that's for you guys to do. I think that will be end of this particular lecture. Okay, thank you.